Hi, I'm Chris Slee. I'm a principal at AWH. We're a software development firm in Dublin. But we're not here for that. We're here to talk about robots. So I'm a mentor on the Marysville First Robotics team. And what that means is I stand back and sort of watch kids make robots. And then if they're doing something that's going to kill them, I might suggest they not do that, right? So probably a good way, if you're not familiar with FRC or FIRST, is sort of give you a background on what FRC is and, you know, if you decide to mentor, what you'd be looking forward to.
FIRST is a family of 4 programs, each level designed to help young people develop new skills, learn how to work as a team, and practice gracious professionalism. In other words, helping everybody, not just your own team, and being a good sport. For the youngest, there's Junior FIRST Lego League, where teams of budding scientists and engineers explore real-world problems, then create a Lego model and show me poster to illustrate their journey. In elementary and middle school, it's FIRST Lego League, where teams build autonomous robots from Lego kits and use research to solve science and engineering challenges. More complicated challenges begin at the middle and high school level. FIRST Tech Challenge brings teams together to build, program, and compete with more sophisticated robots while maintaining an engineering notebook. Then compete with other teams' machines on a playing field. The oldest, most intense program of all is FIRST Robotics Competition. In just 6 weeks, high schoolers with professional engineers as mentors design and build industrial-grade robots to compete with and against each other in a challenging field game, hoping to win bragging rights, recognition, and awards. FTC and FRC participants are eligible for over $20 million in scholarships given by colleges and corporations. At every step along the FIRST journey, tens of thousands of adults are there to help as coaches, mentors, volunteers, and sponsors. Many have come to the program themselves because they believe in the power of FIRST to engage young people at every age level, to teach new skills, build self-confidence, ignite passions, and inspire them to consider choosing science, engineering, and technology as a career path.
10 or 15 or 20 years from today, some kid in those stands will have cured Alzheimer's or AIDS or cancer, or built an engine that doesn't pollute. The probability that one of them is going to do something spectacular that they would not have done without FIRST is almost a guarantee. Look at these kids. They're the future. We're part of it by helping them figure out what to do with their lives.
Impressive. So FIRST is an organization. They've been around since 1989. And with those 4 progressions, we can pick kids up at a very young age and start teaching them the basics of engineering and software. By the time they get to high school, like this group, they are very proficient. So the robot that you're going to see them demonstrate, they built themselves from scratch. There's no pieces and parts to it. So FIRST is an international organization. So it's not just in the US, it's not just in Ohio. There are teams competing globally across regional events. And currently there's about 6,000 teams. So we'll talk a little bit about Central Ohio teams, but there's 6,000 and counting. So every year there's 400 or 500 teams added globally. Some teams drop off. The lower your team number is, the longer you've been in it. So I think we're right around 7,000 is the number that's currently going out. We're 3484, so when you look at a team, you could sort of go, oh, I know how long they've been around in the system. When you go to compete against like Team 142 or Team 28, it's a little intimidating because that means they've been around almost the entire time, right? FIRST is supported by a number of organizations globally. NASA was one of the first, and when we talk about design concepts of the robot, we talk from a NASA perspective of fixed cost, fixed size, fixed weight, and fixed dollars under a fixed amount of time. So NASA set those guidelines up, and those are the guidelines that are still followed today. So every robot has a weight that it can weigh. It can only have so much money spent to build it. So if you're an extremely wealthy team, it doesn't matter. You have to come in with your bill of material, and it has to be under a certain amount. And you only have a short amount of time to actually do the build. So one of the reasons why I signed us up for this talk is because Central Ohio has a number of first teams. There's actually one at Kilbourne that's not there, and Westerville's actually got 3 teams, but I can collapse them into one. So if you're from Westerville, way to overachieve, right? So every high school in Westerville has a team. So if you're near any of these dots and you call those teams, they will want you to mentor because they need adults. Because we have kids coming through the system, and sometimes adults will fall out when their kid graduates from high school. Sometimes mentors stay on longer than that. But programming is one of the pieces that's really missing from a lot of mentors. We've got a lot of engineers. We have a lot of control guys that come in and help. But software developers, which should be most of the people in this room, is needed on almost every single team. So I'm here to sort of shame you and go, if you're not participating by the time we do this next year, well, you're just not trying. So what's in an FRC game, right? So what does this robot do? And we've been asked a couple times out there, what do you do when you play? Now, we figured the best way to do it is to show you this year's game against last year's game. And this robot is from last year's game. So the way that the season sort of works that Drew, our team lead, is going to get into is we go down to Ohio State. We see this video. Of course, there's some other videos and promotional kind of stuff, but we see this video, and then we have to go back to the lab, and in 6 weeks, we have to build a robot based on these videos. So we're going to show 2 videos of this year's competition and what they expected us to do, and then the year that this robot came from and what they expected us to do.
Welcome to the 2015 First Robotics Competition. Here's how we play Recycle Rush. The objective is to build stacks of totes, place recycling bins on top, and recycle litter. The game is played by 2 alliances of 3 teams each on a 27 by 54 foot field, divided into red and blue sides by a step. There are human player stations in the corners. Each side has a landfill zone, an auto zone, and 2 scoring platforms. Alliances stay on their own side of the field throughout the 2.5-minute match, though there will be some interaction near the step. The field and alliance stations are stocked with 3 types of game pieces: totes, recycling containers, and pool noodles, which we call litter. Yellow totes have some reflective tape, which makes robot vision tracking easier. Robots start anywhere on their side of the field, but not in the landfill zone or auto zone. During the 15-second autonomous period at the start of each match, robots use pre-programmed instructions to try to move themselves, yellow totes, and recycling containers into the auto zone. Bonus points are awarded for stacking the yellow totes. Additionally, robots may begin acquiring gray totes and recycling containers from the landfill or step. As the teleoperated period starts, drivers step forward to take the controls. Alliances earn points by stacking totes on their platforms. Each gray tote is worth 2 points. Teams may obtain gray totes from either the landfill, the step, or from a human player via the tote chute. Recycling containers placed on top of scored totes are worth 4 points per level. Robots may obtain litter from the human players via the litter chute. Litter in a scored recycling container is worth 6 points. Litter in the landfill is worth 1 point. Alliances may attempt to throw their litter onto the opposing alliance's side of the field until there are 20 seconds left in the match. Litter, marked with the opposing alliance color and not in scoring position on the field at the end of a match, is considered unprocessed litter, and each piece will add 4 points to the score of the opposing alliance. Alliances may work together to earn a 20-point cooperation bonus by placing 4 yellow totes on the step. Stacking these 4 totes earns an additional 20-point bonus for each alliance. To rank well during qualification matches and advance through the playoff matches to the finals, teams will want to maximize their score for each match. Simply outscoring the opposing alliance on individual matches does not guarantee improved rank. Information displayed after each match will show how the team's performance affected their average score and current rank for the tournament. Of course, robots will need to be built robustly to avoid damage from falling game pieces. Have fun with Recycle Rush and good luck!
Okay, and that's it. You then walk out and go to your lab or wherever it is you're going to build your robot and have to figure out how to make a robot that does those things. So some of the design things you think about is, and we're going to try to make a robot that does all those things. Or we're going to make a robot that only does one of those but really well. You know, those kind of things the kids have to go through. And they end up with lots of whiteboard ideas, and 5 or 6 groups will come in, and then, you know, it really is a sort of a internal competition to see what ideas really start to germinate, and then what direction the entire team has to go, and then actually build the robot. So that was a very manufacturing-oriented, you know, stacking totes, those kind of things. This next video is what this robot does, much more sport-oriented.
Welcome to the 2014 First Robotics Competition and this year's game, Aerial Assist. Aerial Assist is played on an approximately 25 by 54 foot field. Alliances of 3 teams each operate their robots from behind alliance walls at the ends of the field. 2 large scoring goals are located at the top of each alliance wall above the driver stations. 2 smaller scoring goals are at the lower corners of the alliance wall. The center of the field is spanned by the truss, which is approximately 5 feet above the floor. The field is segmented into 3 equal-sized zones: red, white, and blue. Additional goalie zones are at the ends of the field, between the pairs of low goals. Aerial Assist is played with 2-foot diameter exercise balls, colored red and blue to match the corresponding alliance. The objective of Aerial Assist is for teams on an alliance to work together to advance the ball down the field and score into their alliance goals at the far end of the field. A ball scored in a low goal earns 1 point. A ball scored in a high goal earns 10 points. Robots that assist their alliance when scoring will earn big bonuses. The match begins with each robot starting in the white zone or a goalie zone. Each robot can be preloaded with 1 game ball. A 10-second autonomous period starts the match. During this period, robots use pre-programmed instructions. Each ball scored during the autonomous period earns a 5-point bonus. 1 set of goals will be lit up and hot during each half of the autonomous period. Each ball scored in a hot goal gets an extra 5-point bonus. And every robot that moves from the center white zone into their own zone during autonomous gets another 5-point bonus. At the end of this period, human drivers step forward to take the controls. As the teleoperated period starts, teams command their robots to score as quickly as possible. A scoring cycle starts as a human player transfers a ball onto the field. Robots can just take the ball and run directly to the other end of the field to earn the basic goal score. But receiving assistance from your partners in moving the ball down the field will add bonus points. Alliances that use all 3 robots to assist the ball through all 3 zones will earn the most points. Throwing the ball over the truss on the way to a score will add a 10-point bonus, and having your alliance partner catch the toss will add another 10 points. Of course, robots will have to be built robustly to avoid damage from falling balls. Meanwhile, 1 robot in the goalie zone can extend upwards to block shots and defend the goals. Alliances try to score as many points as they can during the 2.5-minute match. Good luck, and we'll see you at the competitions.
Yeah, so that's a little bit different than the tote stacking, right? So this was a fun game, very sport oriented. So again, you had to make design decisions, right? As to what kind of robot did you want, what did you want to participate in, how are you going to pass balls back and forth between your teammates, and your teammates are selected randomly and rotated randomly at every competition. So you can't even call another team and go, hey, let's pair up and you work this way and we'll work this way. It's random. So you have to design essentially a robot in mind that either does everything sort of okay, or it does like one or two things really well, right? So you see those videos, you go back and you have, yes? You're allowed to have contact, but what you're not allowed to do is change their behavior, and flipping them over would change their behavior. Right? Yeah, you can't hurt them, right? Although we broke the front end of this robot by ramming it into somebody, so yeah, well, we were more defensive, sort of linebacker kind of thing. So you get 6 weeks. You get 6 weeks from kickoff to robot, which is 6 weeks from kickoff to robot from scratch. There's no kits. There's no plans. There's nothing except for going to a whiteboard and then building what you want to build, right? And so if we look at 6 weeks, you know, for agile developers, that's 3 sprints. You get 3 sprints in order to build a robot, right? Code, design, out the door, you know, that kind of thing. If someone came to us and said, hey, we want you to build a robot, but we only had the budget for 6 weeks, we'd go, no, we can't do that. But we have a lot of free high school labor, so we can get there. 6 weeks is also the amount of time it takes a kitten to develop a personality. Because you have to have a kitten in every slide deck, right? It also is how long it takes for a bone to heal. So if you've ever had a fracture, that's how long it takes. That's how long you get to build your robot. It also, for some reason, is exactly how long it takes to get a passport. Because I'm not sure how building a robot and the amount of time it takes to get a piece of paper printed and sent to you is equivalent, but those are your times, right? So what I'm going to do now is turn it over to the team. So you won't hear from me again. So the team's now going to take over. I'm going to introduce Drew, who's going to introduce himself, and then he's going to pass it down. And then each one of them is going to drive from this point forward. Have a good day.
All right, so I'm Drew Musto. I'm a senior at Marysville High School. I'll be graduating in actually about 20 days, so woo for that. I'm going to college at The Ohio State University for computer science and engineering, and I participated in the club for all 4 years, in basically every piece of the club, every part of the club, and this year I was the team captain.
I'm Dominic Oliverio, and I've been participating in FIRST for 1 year now, and I'm a sophomore at Marysville High School.
Hi, I'm Bronson Brown. I'm a sophomore at Marysville High School. I was the lead programmer this year.
I am Joseph Peck. I am a senior at Marysville High School and a 4-year veteran of the robotics team, of which I have led 2 years as captain of the chassis.
All right, so our first video is actually this robot in action. This is the autonomous mode. So in that video, to explain a little bit, autonomous mode is 15 seconds at the start of the match where your robot is pre-programmed to do an action. So no drivers can touch the controls. So if you look here, our robot's right there in front. It says 3484 between the bars. Watch the ball as it goes. It has a very interesting trajectory. So, and every year at FIRST I've been in, I've never seen a shot like that in my life. So I was really proud of our robot because he really toughed it out after missing a shot. All right, so this is our team this year at kickoff. It's a voluntary event. Looks like there are about 15 kids there, so that's like 15 out of 20-ish, you know. It's the first Saturday of January, so for example, this year it was the 3rd. You go down to Ohio State. I think there's one in Cleveland. They're all over the world, really. It's a global broadcast where each team will get it at the same time, so there's no advantages based on where your time zone is, or you can't look it up on the internet, you know, and get a little sneak peek of what the game is. At this event, they will not only give you the game video, but any new toys they have you. So every year you get a stock kit of parts. And every year they'll update you on what's new, what's old, what's up. So like, for example, this year we have a whole new control system. So they had a good 20 minutes where they were explaining all the different control systems and what's new with that. This is our basic team organization. So if you look at the top, all three at the top is our non-technical categories, which are, we call them business, marketing, yada, 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 not robots, basically. So what they do is they work with our sponsors with community outreach, fundraisers, demos. So for example, this would be a demo. We're going our robot, we're showing everyone what's up. We're sharing our wonderful experience at first with everyone. So we're not just a robotics team. We are a club. We do a lot more than we just have a robot. We've taken it to malls, we've taken it to all the local schools, we've taken it to even Fairbanks, which isn't Marysville, but it's kind of Marysville. So we take our robot really everywhere, and they help us just get money and show it off because it's really cool. Then we have our actual student categories, which are chassis, game component, wiring, and code, and then we have integration above. So as team captain, I was a lot of the integration where I make sure everyone's on track, everyone is working good, everyone's working well together, everyone makes sure that it all fits together. Because when you have these subdivisions, you kind of have one group they're just going really, really hard and they're building something awesome. And then you go and you put it all together and then you find out that, it's a puzzle, but you're missing a piece somewhere. So you can really screw yourselves over if you're not careful with that. So for our first group, we have chassis, which is, if you look on our robot, it's really any of the big frame of the robot underneath all the metal pieces on top. It's the drive system, the frame, the electronic layout. So a big part of their job is to see, okay, we have a drive system. What is the best to do? So for example, this one is a tank drive, which means that there's one motor on each side of the robot that powers a wheelbase. So this is really powerful, really strong, but it's not very agile, but we can push anyone around ever, so it's really cool to have. This year they had a really big challenge. It was our first year we used Mechanism, which is a type of system where each individual wheel has a motor hooked up to it, and they have a diagonal force vector. So with that, you can power different motors differently to move your robot really any which way. So you can move it like a D-pad, up, down, left, right, and then you can also free spin or really do whatever you want with it. It's a really cool system to use, but it's not a cool system to program. Then we have the game component, which is one of the most interesting groups because every year you're changing. So for this year, they had to build a way to load the robot and a way to launch the robot, which is a lot harder than it sounds because we have certain specifications we have to comply to. So for example, the sizing is a huge issue and the weight is always a huge issue. This robot weighed in at 119.8 pounds, and the weight limit is 120 pounds. So it's always very close every year. Any team you talk to, they'll go, man, we were half a pound under, we were half a pound over, we had to cut this part off, and it's just a mess. Then we have our wiring team, so what happens is drive team, game device team, they'll go, okay, we need 6 motors here, we need 4 motors here, we need this special motor here. And so they'll lay it out on a test board, and they'll kind of figure out where everything goes, how to wire it up. And then they have to work with the chassis team on where everything will actually fit in the robot, because they obviously can't just have a big board and we just drill it onto the robot because it won't fit, and it'll be really awkward, and it just won't work. So they have to move all the components from that board to the robot, and it's honestly challenging because there's so many different surfaces you can apply all the electronics to and where you can put them. So that's fun. Then we have coding, which I'm sure none of you are familiar with here. So for our coding, we actually use LabVIEW. It's by National Instruments. It's a block function language, so it's a little bit different than anything you guys have probably ever used. But it's optimized for first, so it's really nice for all the teams to use. And then we have, also it's really difficult to be a programmer in this program because what happens is we'll go, okay, it's week 5, our robot's done. How are you guys doing? And they'll be like, well, we haven't had anything for 5 weeks, but I guess now we can program. And so it's really interesting because we can kind of go, well, here's the systems we're going to need. And they're going to be like, okay, well, cool, I'll program it. And then we'll get there and we'll be like, oh, yeah, we changed like 4 things along the way. So can you just go plop in and change that real quick? And they'll be like, And then the backbone of the entire team are our mentors. So we have mentors in every part of our team or our club. So we have mentors for the business side. We have mentors for chassis, game device, wiring, programming, development, whatever. Even Chris over there, he does a lot with administration even. So he helps me a lot, make sure everyone's doing everything right, and we're all working together well. So as you can imagine, when you have 20 teenagers working together for 6 weeks in a room, tensions can be a little high at times. Yeah, mentor, mentor, mentor. All right, so this is actually a wonderful picture of part of our business team doing inventory. The first day we all sat down and we planned our robot out. They were sitting there going, wow, this sucks. What can we do? So I stuck them on inventorying, and now they hate me, and they go to the library instead of working in the lab.
Right, this is our chassis team. Each year, like Drew said, we are in charge of drivetrain and basically the layout of the robot where everything is going to go. This year, the chassis had a bit of an issue considering the fact I was the only one on the team that was actually part of the team the previous year. The other 3 people you see up here were freshmen. So on top of teaching them how to design the robot, I had to teach them how to use every tool. This is for the chassis. You have 3 different pretty much 3 different categories. This is one of them. This is the basic design of this our chassis right here. You can see where we lay out the robot, and this is actually in CAD, so that we can pretty much have a virtual diagram of what the robot will look like to see if it will actually fit together, because you don't want to cut the pieces and then realize they will not go together. And then at the very end, you get fabrication, where we send out all our blueprints to a company and they will make our frame. This year, we're actually hoping that we don't have to ship it out because we will have a fabrication area right in our lab. I will hand it off to Dom to explain the game device.
All right, so as you can see here, we are on launch day, and we're designing our new ideas on the whiteboard. This is about 2 hours after coming home from OSU and watching that video. And this is the very rough design on the whiteboard, and as you can see, it's come a very long way from on the whiteboard. And this is our first prototype of this robot here.
All right, yeah, so this is wiring. As you can see, we have all of our new controls. This is new, that's new, this is all old. But so that was a huge challenge for wiring this year, because everything they're used to got totally thrown in the trash can, and they had to completely just learn a whole new control system. So I think this is the first time they've ever done that, but it's really nice because it keeps it updated with all the current robotics, and it kind of, honestly, this is a lot nicer than the old one. In the old one, it was like this, but they had cards that you had to put in and like program them differently and wire them differently based on what you needed. So it was kind of weird to have, year by year, you'd like change out the cards. So it was a really kind of weird control system. And this is a lot nicer. So it was really cool to play with this year, but it was also very not cool to learn it. Yeah, so this is on our current robot. This is our first kind of wiring day. What we did is we had a test frame where we had wires everywhere, and it kind of looks like it did now because we had to rewire this one. But they were just literally wires everywhere. They were like a huge rat's nest, bird's nest, whatever. And it was a huge pain. So what they did is we ordered 2 frames. This is our second frame. And what they did is they put the wiring strips in and they labeled everything where it's going to go. And then they actually cut the wires to length. And everything looks really nice. So it's something really cool we did this year, which we've never done before because normally we just have a huge rat's nest. But that's really cool.
So this is a clear example of us deep in the process of debugging code. This year was a little difficult. This is the first time I've ever seen LabVIEW. Same for the other guys. So we were literally just figuring it out as we went. There was a lot of Google involved, a lot of mentor help. But eventually, after we got commands from other people, different parts came in that we were able to program. 6 weeks later, magic happens. So it's pretty special stuff there.
All right, so another huge thing is that in FRC, we can't just outsource every part because we do have that money limit. So a lot of the stuff we do, we have to engineer with suboptimal tools. So as you can see here, we had a problem with our wheel. Our hub was actually a little bit too big, so it was interfering with some other stuff, so we had to grind it down. And as you can see, it looks very safe and very friendly. All right, so this is us testing the robot. This is actually our first test after we got everything working. So we're still kind of in awe.
Pass it back. Oh, that's loading it. Oh, success. You're gonna get hit. Go ahead. Woo!
Yeah, so as you can see there, that was just a very rough test. It didn't shoot it very far, but we were just testing it for its capabilities. Because I don't know if you guys can see this, but on there, those little black blocks are actually huge torsion springs. So they pack a lot of power. So we needed to be very careful when we tested this because we could actually tear our robot in pieces just with those springs. Yeah, so this is us. We're loading our robot. We're loading all of our tools. We're loading everything to go to the competition. We have to load basically our entire lab into an 8 by 8 foot square, or 8 by 10 foot, I think it is. For the competition, we have an 8 by 10 foot square to actually work in and test our robot, work our robot, anything in between matches that falls off or breaks. So at competition, if anything does break, it's very hectic because there's actually a point this year where we had 3 games back to back where we couldn't even go back to the pit. So we were sneaking wrenches and Allen keys on there trying to tighten stuff up in between matches, and it was a mess. Yeah, so this is us actually in our pit. As you can see, we don't have a lot of room. Right there, that little cabinet to that little table over there is all the room we have in between. So it's very tight, very close quarters. We only can have like 4 or 5 people down there. Otherwise, we're just packed in like sardines and we can't do anything. So we normally kick our developers into the stand, and everyone else is trying to smash the robot with hammers to get it to work. And then there's another picture of us working on the robot. They're actually retying the paracord because, as you can imagine, that spring puts a lot of tension on the paracord. So we're trying to retie it as much as we can because we don't want it to become loose, because if that does snap, there's a huge safety risk to anyone even near the field, because that thing will tear itself apart. It'll launch metal pieces everywhere, which I can imagine lots of people do not want in their eyeballs. Yeah, and so another big thing is that you talk to the coaches and the safety captains. They have actual safety people there. Those are the judges. So they will get a little bit of background on our robot. They'll test it to make sure our robot's safe to perform. They'll kind of get a little bit of a rundown on our robot. They'll write it down. They'll keep it in records so they can kind of see year by year how the team progresses or how they don't. So it's kind of cool because there actually is a little bit of a backbone. And then also another thing about the coaches and judges is if something's wrong with the robot, you can go, hey, none of our mentors know what to do. We don't know what to do. What do you think? And these guys have been working in FRC for 10, 15 years, so someone there is going to know what's wrong, and someone can help you. And this is actually us lining up for a game. That's us right there. Those are the balls. This is us just lining up. So you can have, in the game, you have 3 teams per alliance, like it said, and you have 2 drivers, a coach, and then 1 human player. So the human player can actually interact with the game pieces. So, for example, the ball is a game piece this year. And the drivers you can have 2 drivers, so we always do 1 to actually drive it around and 1 to perform any of the game device functions. So, but it's up to you. You can have 2 drivers, they can do whatever you want. Yeah, so now we're going to go into a little bit of the control systems and a little bit of the programming to give you guys kind of a deeper look into that. At the top here, we have a Robo Rio, which functions similar to a Maxi Raspberry Pi. So it's a lot nicer to use than our old control system because it was just kind of wires everywhere. You had to have a bunch of, they were called sidecars and different controllers and relays. And with this, it's all packaged into one, and it's all super intuitive and easy to use. So that's really nice this year. This down here is a pneumatics control module, so you'll plug all your pneumatics into there. Pneumatics is kind of like hydraulics, but it's with air. So, for example, you have pneumatic pistons, pneumatic cylinders, pneumatic switches. And you plug all that into there, and it'll regulate what to do, when to open it, when to close it, when to extend, when to retract. Then we also plug in a compressor. We have to actually compress our own air on our robot because we use so much of it throughout the competition. We can't just charge it up before. Oh, sorry. This is a power distribution board, which plugs directly into the battery and powers all of our onboard systems. And that's with the 12-volt battery. They're regulated. They look like just a big orange block, not orange, big gray block. And then Dominic.
All right, so up here is a motor controller, and it regulates the speed of these motors by turning it on and off really fast. And down here we have a solenoid, and it controls the flow of air, kind of like a motor controller except for pneumatics. And this is a pneumatic piston, and as you can see on our robot, it regulates when this thing goes up and down. We also like to call it the big rod.
Some of these programming languages may seem a little bit familiar to you guys. LabVIEW was most common in FRC just because it's been around the longest. National Instruments does a lot of collaborations with FRC. They've been in the program for a long time. They also produce the brains of the robot. So it's all very compatible. That's why it's most used. C++ is the second most used. It's around about 10% of the teams use C++. It's growing definitely in size. There's a lot more people this year using it than they did last year. Java just got introduced to FRC this year. They're just starting to release manuals and libraries that you can use compatibility with FRC products. And there's not a lot of people that we talked to that actually used it. And a matter of fact, there wasn't any people at the competition that we went to that we talked to who were using Java, just because it's new and very complicated to use as of now. But definitely as we progress in time, you'll see a lot more people using it. We have Python up here. There was only one team who used Python, and they just took an API from C++ and applied it to FRC to be able to run their robot. We're not really sure how that worked out for them, but we know that they got it accomplished, and so that was that. This is an example of LabVIEW. I don't know how, I'm sure a lot of you are familiar with LabVIEW. It basically, it runs, for those who aren't, it runs left to right. It checks for prerequisites. If there's not, then it just runs what's in front of it. FRC breaks it down into a format of basically 3 individual palettes that you need to actually manipulate. There's begin, there's teleop, and there's finish at the end there. Begin, anything that's on the robot at all needs to be initialized and begin. Anything that's running in real time, it updates every 20 milliseconds. It checks your teleop. It checks for control values, buttons being pushed, and it feeds it directly into a function that will feed into a motor controller that will run pulse width modulation to it. And then finish is just wrapping everything up. So when you shut down your robot, make sure everything's closing down. This is an example up top here of a drive system. You have your joysticks feeding into the value, which feeds into a function that they name tank drive. It's preset, and it just feeds into our all of our motor controllers there. This is an example of an air compressor working. There's the solenoids being established, solenoids feeding to a function, which gets input from these buttons here, and then this is just everything wrapping up.
All right, so big thing in FRC is that we're preparing kids for the future. We're preparing them for college. We're preparing them for going out into the real world. Like, for example, on the NASA Curiosity rover, there were, I think, 4 former FRC members who worked on that. And so they're always trying to innovate with FRC. And we think the big next innovation is freaking laser beams. So I don't know how many of you guys saw this, but the NASA, they actually had their M-Space warp drive where they think they actually launch particles faster than light. So we're very interested in how FRC is going to integrate that. We're thinking next year we're going to be building spaceships, so who knows?
Back to me. All right, so what we're going to do now, if everyone's copacetic with it, is turn the robot on, run it around a little bit, and possibly shoot the ball out of the audience. If you get hit by the ball, there's no culpability on our part that you got hit by a ball at this particular thing. So let the guys start driving.
Yeah, we can. So we actually made a modification to our robot. We took some parts off, so it actually shoots a lot more linearly now. So we're gonna have a little bit of a test shot to see how exactly it functions in this room. So be very careful. It does fire very strongly, very fast.
Let's not shoot it at the dog.
Hey, play fetch.
Hey, that laptop, Dominic, with your life.
All right, so as you can see here, we loaded the ball, and now we're lowering our catapult mechanism. Or we're trying to. We have to build up air pressure first, so we got to wait a little bit for it to build up air pressure. Yeah, so we're just going to manually do it. Normally, we have the 15 seconds plus. So now that it's loaded in, we can actually lower our mechanism more, or we can try to.
So you got to spin it to get it up.
So again, this is our robot from last year. So our drivers graduated last year, so this is a little bit of a... It's a bit of an experience right now, as you can see. But yeah, we still need to build up air pressure. So, does anyone have any questions I can answer while we're building up air pressure? No? All right. That means I did a good job presenting. Oh, you? The robot has a budget of $4,000. You have to, like you said, you have to submit a bill of materials, which is everything, including fabrication that your robot did. So, for example, our robot this year, I think it clocked in at 3,500. This robot clocked in closer to just 3,000. But that's not covering costs for the lab, for any tools you use, any auxiliary fabrication, really anything. So normally per year we say we need around $8,000 to $10,000 depending on how much money we want to spend. I mean, if you give us $100,000, we'll spend it all, don't worry. But $4,000 is for the robot, and then everything else. Yeah, so you get a thing called a kit of parts. It actually comes in that green container over there if you'll look. For example, this year they gave us all of our new control modules, and that's just so that we can order that off a website called AndyMark, which it's a lot of the stock FRC parts, and they'll give you like a sim motor every year and a new battery. So they'll give you a lot of the base stuff, but like all the metal and anything we need fabricated or especially created, we have to buy ourselves. No, the kit is free. It does not count in the budget. That's a big thing. Because the control components themselves cost probably about $1,200. So if we were to buy that and include it in our bill of materials, we'd be severely limited in what we could build.
Yeah, because FRC wants every team to use the control surfaces the same, because they actually take over when you're out of them, you plug into your network and you actually control your robot or when it turns on.
They're about 42 PSI, so we should be good.
Yeah.
Okay.
Enough.
I was just waiting.
So that way you only have to worry about periodic tasks, those kind of things. But as far as when they go, okay, you guys ready? And they turn the whole course on, right? Everyone has to be talking the same network. Everyone has to be talking the same controller. So they give us that. They give us the power distribution. They give us regulations on how much power you need. And then they give us the compressor modules. They give us regulations on how much pressure you need to run. Like this, we swapped out this compressor module for last year. Last year's compressor module got swapped out for this year's compressor module. And it produces less air, so it takes us longer. Because normally last year we would turn that on within almost 3 days, around 20 times. This one will take a while.
Yeah, so to compare that, we're at about 45 right now. So as you can see, it's very, very slow.
I don't know where it's exactly go.
Yeah, so that was about a half cock. So the farther we cock it back, the higher it will actually go. And we actually had 2 of these on top, but we broke them off during one of our other demos, and we haven't replaced them because we've been trying to build our other robot. So it actually fires a lot more linearly than it did at the competition. Or in that video we showed you guys, as you saw, it got some nice airtime. Yeah, so as you can see, not enough air pressure again. Like I said, not like I said, but we actually, a week ago, we sat down and we discovered that our old C-Rio, which is the precursor to the Robo-Rio, it had an unrepairable error, so we had to replace all of our electronics with the new control systems. So that was a huge undertaking, and now we just discovered that the air pressure is not sufficient enough to really work this robot at the pressure we need it. You need to bring it back more, Joe. Then that means we also had to rewrite a lot of our code because all of our pneumatic systems changed, like you said. So we used to have relays and sidecars, and now we just have one system. So right now, like not even half a week ago, yeah, we had to rewrite all their pneumatics code, and now it's just a lot different than what it's used to. At the competition, we just load it up, we'd fire it easy, but now it's not so easy.
Just give it some more. It needs to build up pressure. You're using too much of it. Yeah. So you guys have questions? Yeah.
Do you have any YouTube videos like you just showed us here? We can look at to see the whole competition.
Yeah, if you just YouTube FRC 2015 or FRC 2014, there are thousands because there's 6,000 teams. Everyone's producing videos. There's a lot of how-to. Some teams have some of their kids sit down and do tutorials, and they film that too. So, like, oh, enter the LabVIEW, and you know, it's part of their program, right? So we're about 4 years old as a program. The team sort of reset coming into this year as far as almost all the seniors left, and we were left with like 3 kids. So we're rebuilding the team right now with younger kids. So, but yeah, there's tons of stuff out there.
If you really want to look up FRC videos, you can search like 2014 FRC Grand Finals, and that's the top team from every region competing in St. Louis. So that's probably a good thing to watch if you want to see a very competitive, high-level game. Yeah, so I was talking a little back, farther back a little, so you can see how I got a little bit more airtime. I think in total we had about.
No, we're agile. We don't do it by
JK. Last year we had about 15, and this year we have about 20. But again, that's students at different levels of involvement. It's a completely voluntary program, so we'll have students who show up once a month. We'll have students who show up every time. We'll have students who go home and that's all they do is FRC for those 6 weeks. And we'll have students who don't even think about FRC when they're home. So it's a little bit hard to gauge how many students are actually on the team. But for this year, we had about, I'm going to say 15 kids again. But in total, we had about 7 or 8 kids who are really dedicated to the program. So what we do is we have our base groups. So as you saw, game device, chassis, wiring, etc., programming, development. And then those kids will kind of just float in and out and do what they can. Really, they're almost a liability, but we still want them involved because we've actually had kids that 1 year they're not involved at all, and the next year they come back and they're super excited about the program. So it's cool to see how they change year by year a little bit. I think a lot of that is the first year they're involved, they're really shy because they're like, well, I'm just a freshman. I don't know anything about robotics. Then next year they go, well, I still don't know anything about robotics. I'm a sophomore now. You know, maybe I can involve myself a little more. Maybe I can apply myself. Yeah, there's a lot of team dynamic. It's interesting.
There are some FRC teams that have 100 kids, but when you talk to the coaches, there's a core of 15 or 20, right?
There was one team we saw. They actually made a parody video of Bohemian Rhapsody for FRC, so you can imagine they probably had about 100 kids. And if they can have 15 kids go and make a parody video of Bohemian Rhapsody, they probably had quite a few kids.
Yeah, so Marysville this year is starting an FLL team. So we'll have the Lego kids that are in the intermediate and middle school. So we'll have one of those teams. And then the following year, we're splitting that, pushing the Legos down to just the elementary school. And then we'll put in an FTC team in middle school. So that'll give us a nice progression of students with who have some experience going up. Yeah, it's not back far enough. Oop. Okay. Okay. You can do it, Joe. All right. So when you use that much air to move that arm, you don't have enough air to run that other solenoid, right?
Yes.
Can you tell us a little more about the block language that you use?
Bronson can.
So the acronym I like to use is I'm just gonna say functional real-time graphical language. As I said before, it runs left to right, essentially, more or less. It checks for prerequisites. So if there's something before it that's wired in that has to be accomplished before the next task can accomplish, it'll run that task and then follow the order down. So it's mostly used by having different functions that perform different tasks. And then they're wired together, or like wired with a little string. You connect them, and you basically then just get values that feed into the different functions, and basically tells it when to do what. So, for example, on a motor, if we just have a singular motor, there's a function that tells what to do on a really, really complex level, where I am just taking an array that is assigned to joystick values. Hold on just a second. Where I'm taking a array assigned to joystick values and feeding them into the smaller function, which feeds into the actual robot and runs pulse width modulation, tells it how long it should be running and how long it shouldn't be to get the effective speed that we want. Any other questions?
That's actually a custom gearbox. What we did is we ordered that off AndyMark, and we stuck a ratcheting wrench in there. So we actually manufactured our own locking mechanism. So there's a little pin in there that'll actually slide into the gear, and that ratcheting wrench will hold the tension on it so that it can't rotate back. And then we have a pin that pushes that it's like a bar in the middle of the gear. So it pushes that out, and it unlocks it from the gear. It disengages it so that the gear is in free spin. So the cylinder on the end will just free spin and release all the pressure onto the springs. We're actually going to run it back and forth a little bit to show you its speed, because this thing is a monster. So this is in first gear, which is what we ran in 99% of the time. This means it has about 9 billion pounds of torque on it. Just a guess, you know. And but it's not as fast as it could be. So I don't know if you guys know about gearboxes, but what it is, it's a trade-off speed for torque. So the faster it goes, the less torque it has, which means that the less power it has. So the slower you go, the more torque it has. So in this first gear, we have not as much speed, but we have a lot of power, which is what we really wanted in the competition, so we could push other robots around. In our legacy code, I don't think we kept the second gear option on it, so I don't know if we can engage it into its second gear. Yeah, we took it off. What kind of battery pack do you use? The battery's in the front. You can't really see it, but I'll bring one out real quick. We have an extra. It's this right here. It's basically just a big, here. It's just a lead acid battery. So it's 12 volt lead acid battery. It's FRC standard. It's all boxed up. Every team uses them. You have to use it. It's FRC regulation. Any other questions? It depends on the power of the robot. So I know R1 this year, it could not run as long because we had a lot of different components and we had a lot of weight on like the strain of the drive. So it couldn't run as long as this one could. With this one, our biggest concern is that we actually have motors that will overheat very, very rapidly. Yeah, Joe, can you stable it? Yeah, so for example, in January, we did a demo with this exact robot, and we almost burnt out our motor where it was running for so long that it smelled like burnt pancakes. So we quickly deduced something was wrong because we didn't think they would be burning their pancakes. And we discovered that the motor was about 4,000 degrees and burning itself out. So now we're very careful not to burn out any of our motors. And yeah, so for right now, I can read the battery percentage. Maybe. It says it's about 11.5 volts right now, so it's still a bit. Normally, when you start dropping 6, 7, even a little bit of 8, you'll start getting like power outages almost. where your robot won't function as normal because it doesn't have enough total volts for the entire systems of the robot. So you'll get like really jerky and like in and out controls almost. So it's not so much the battery's dead as much as it doesn't have enough capacity to run the entire robot at once. Huh? Yeah. We do not currently. We have no use for it, but we can actually. There are actually encoders within the FRC that we can attach to axles that will tell us how many rotations per minute we're getting. So we used one on our. We had a robot 4 years ago where it was a ballista, so we'd actually encode the chain on that to see like how much power we get in it and see like how far back we need to be and like calculate the trajectory almost. So we could do it if we wanted to, but it's more programming, it's more wiring. So the less we have to do, the better. We only have to if we need to. Any other questions? You right there, yeah.
Is there any specific software application that you guys use to develop your systems? I mean, is there something associated with this program that you guys developed?
No, it's really just LabVIEW. That's really it. It's there's actually a whole library for FRC that you download from LabVIEW, where they have a lot of the basic functions on there. Like he said, you have the drive function, which is an FRC in the FRC library. So again, that's the easiest way to do programming for FRC.
You mentioned C++. Can you interface C++ to the National Instruments library? Is that what you do?
Yeah, there's a someone wrote every year someone writes a wrapper during beta, and then they publish that wrapper, and then if you're doing C++, you just use that.
So in lieu of the graphical user.
Exactly.
You have 4 motors here. Can you explain how they drive them?
Okay, so for our drive system right here, we actually have 2 gearboxes, one for each side. It's called tank drive. So one joystick functions one side, one wheelbase, one side, and the other does the other. And so those gearboxes are hooked up to one wheel, and they are chain driven to the other 3 wheels. So we have 4 wheels on each side. Within that gearbox, we actually have 3 of the stock motors hooked up for each gearbox. So that means we have 3 times the power or speed of a normal robot in the competition. So our max speed was something around 20 feet per second. So it was killer. Yeah. Any other questions?
That was a real impressive move when I saw there in the video where you shot the ball, it missed, and then you recovered and you kind of ricocheted off of your machine here. Was that planned in terms of?
Well, of course it was.
It was a happy accident. So what happens in autonomous is in that game mode, you got points for scoring the ball, and then you got points for driving forward. So our robot was planned to. So another thing is you have to be within the dimensions when the game starts, and then you can go out. So our loader has to be up at the start, otherwise we're not within the rules and regulations of the game. So we had to start with everything packed up. Then we bring our loader down, cock our catapult back, and then we shoot and drive forward. So what happened was we were just a hair off on our placement, and luckily the ball bounced back and bounced back again into the goal. Well, the problem is we actually hand set it on the field ourselves. So we had the calculated trajectory with the spring power and everything, but it's a little hit and miss depending, on where we set it on the field itself. We get feedback from the battery and. Yeah, well, we can also attach a camera. Oh, yeah, we also have a limit switch.
We can. You have to probe something, but I don't think you can actually. You can run things with probes on them, but it slows down the whole process in general. But when you're running things, you can see exactly what values are coming in and out through to what functions.
You can rumble the joystick if you want to.
When you get to set point, you can rumble.
Sure. Yeah. It's safer to actually put physical limitation on the robot itself. So like that arm, without a limit switch there, that wrench will drag that arm back down into the winch, and then you can never let it go. Right? You have to take it apart. So there's limit switches on there that with a little bar sitting out there. So as it comes down, it'll touch the limit switch, and the limit switch will turn the motors off. So the code, even if the users going, keep going, that it just won't happen.
Yeah, there's a little dashboard where we can get a little bit of a feedback. So we can, like, if we had an encoder, it would be there, and then we can also have like a USB camera we can hook up, and we'll have the camera right there as well.
Are those springs from a piece of farm equipment?
Those springs are actually custom made from a shop in Texas. I would know because I spent 2 weeks sizing, pricing, and trying to find the right person to ship them to us on time. It was a huge pain, and we're never doing that again. And actually, a funny thing is, I was reading the updated rules for this year because there's a little list of all the rules that updated and changed. And there was actually a spring size limitation this year, so I wonder why they put that rule in place. Any other questions? We're almost done, and then we have lunch, so we'll probably hang around too, so if you want to come down and ask us by yourselves.
So how did you guys do in the competition last year?
Last year, this robot is a 3-time semifinalist where we got screwed each time. So at our regional competition up in Cleveland, we are in the semifinal, and the score was 1-1, their best of 3s. And one of our robots had a technical difficulty where they could not perform, so they put in what they call a sub. So in that substitution, that robot also had a technical difficulty, so during the match, it was a 2 versus 3, and we lost by 10 points. Then we went to the state competition, where we were ahead by some 40-some points. It was like 120 to 80. And then we learned that they miscalled a foul, so they took 50 points away from us and gave it to the other team. So that was not very good. We were a little bit mad about that.
Under gracious professionalism, you don't want to stomp another side, right? So when we got that far ahead and it was 30 seconds left, we went, okay, don't score anymore.
Yeah, we kind of played a little bit of keep away. Yeah, so we learned our lesson. And then we went to it's called CORI, Central Ohio Robotics Initiative. It's at Dublin Kaufman. If any of you guys want to go there, that's a really good way to look. It's a very casual event. Teams just go and they have fun. And then we got to the semifinals again, and we actually lost our last game on the 3rd tiebreaker. So, yeah, that was a little bit, we were a little mad about that as well.
How many robots do you build per year?
We build one per year. It's a year cycle. So January to mid-February is build season, and then we wait about a month for our competition. We have to bag it up, tie it off, and have it notarized that it's bagged up and on time. And then if it's found out that you fabricated anything, then you get disqualified. And then past that, we can go to off-season events or off-season anything. You can just relax, not do anything on the off-season. A lot of the off-season, we work on our sponsorships and community outreach. So community outreach, obviously, right here. We'll go to our sponsor businesses. We'll show our robot off. And then normally November to December, we have new training. So anyone who wants to learn something new or anyone who wants to learn anything, we'll kind of train them on how to do, because you have to think, you have freshmen coming in who don't know a thing about robotics, and in 3 months they have to build a robot, so it's kind of difficult to coordinate. Any other?
You guys are getting us right now for this?
Yeah, we actually are.
All right. So any more questions, just come down and the kids will be able to answer them. And, oh, thank you.
You mentioned there was a technical failure and then you had to bring in another robot. That's why I wondered how many there were. But that was another team. That was another team. Because it's 3 teams. Instead of 3 teams, like team A, B, C, robot.
Cable wise. They're on the far side. No, I understand. Yeah, as soon as they clear out. As soon as they clear out, we'll bring this cable and the other cable on here. Yeah, bring them out. Do I need to turn off this laptop?
Why don't you use some other random team?